Back in 1749, Benjamin Franklin first used the term battery to describe a capacitor setup he had built for his experiments into electricity. It was actually a string of metal-coated glass panels that were charged from a static electricity generator, but Franklin used the term battery to describe them from the original meaning of the word, two or more similar objects functioning together to achieve a particular task. It would be another 51 years before Alessandro Volta assembled the voltaic pile, pairs of copper and zinc discs piled on top of one another, separated by layers of brine-soaked cloth. It was the world's first true electrochemical battery, and in the 221 years since, battery technology has come on in leaps and bounds. And of course, in the electric vehicle world, we've relied on the continual development of batteries to help produce electric vehicles with increasing capabilities, power performance, and range per charge. From the primitive lead-zinc batteries of the early 20th century EV through to the most cutting edge of lithium-ion cells found in most of today's production vehicles, automakers and electrochemists alike have sought to find the holy grail of EV batteries. Cells that offer the highest energy density, lowest overall weight, highest discharge and charge rate, longest lifespan and lowest cost, along with a higher margin of safety. Because of increased interest in electric vehicles, driven in part these days by the urgency to find a more environmentally sustainable solution to our planet's transportation needs than internal combustion engines and fossil fuels, our inboxes are regularly flooded with press releases and news tip-offs about some new amazing type of battery tech. From rechargeable metal air batteries to solid-state, nano-coated electrodes, and super-fast recharging tech, each promises to revolutionize the world of EVs. They promise a future where electric cars can travel further per charge than today's modern internal combustion engine vehicles on a single tank of fuel. They promise to smash through the price parity point with ICE vehicles. And they promise to use raw materials that are far easier to mine and pose far fewer ethical human rights concerns than today's battery cells, many of which use some percentage of cobalt, a metal that is often mined in less than ethical ways. While these new wonder chemistries promise us a glorious future for electric vehicles, not to mention the knock-on benefits to consumer electronics, and in fact anything else that relies on some form of battery to function, but it's often difficult to differentiate from the headline stories that detail laboratory breakthroughs in battery tech to actual production batteries that are on the market or have a clear path to marketability. And all too often, new battery breakthroughs, met with incredibly high levels of enthusiasm and excitement in the press, seem to vanish, never to be heard of again. And even when established brands like Tesla announce new battery technology, as Tesla did last fall when it revealed its new 4680 form factor cells, there's often a lot of confusion as to why it's taking so darned long to bring those new battery cells to market. And that's before we even look at the troubles currently facing LG Energy and the companies that use LG Energy as a battery supplier of choice. As I'm sure most of you are aware, Chevrolet, Hyundai, Porsche, Audi, and Ford have all suffered issues with LG Energy supplied battery packs. And for some owners of those cars, including me, the time it's taken to figure out what's happening to battery cells to lead them to fail can all too easily feel like automakers and cell manufacturers aren't taking battery problems seriously. The reality though, making electric car batteries is hard. So today I thought it would be good to go through some of the challenges in bringing new electric car batteries to market, explain why it's harder than you think to get batteries into production in the first place, and then explain why, when there's an issue with a car battery pack, it can be a tough thing to track it down. If this sounds like a familiar topic from us, it's because we did actually make a video previously detailing the challenges in getting batteries to market. But today I want to focus on the getting batteries right part of cell development. Oh, and before we get underway, if you want to see the excellent video Kate did a while back on the big challenge of making sure that cobalt is ethically mined, you can see that here. And I'll leave a link in the video description below in case YouTube cards are not working. As I've previously detailed, there is a massive difference between the laboratory and series production lines when it comes to battery packs. That's because it's relatively easy to make a prototype or demonstration battery cell as a proof of concept. Electrochemists are doing it every day in laboratories around the world. Back when the first lithium-ion cells are developed in the laboratory in the mid-1980s, the majority of development work relied on physical experimentation to find the best combination of materials to produce a stable, successful cell. Luckily these days, computer simulations can rapidly speed up the process, using known physical characteristics to model thousands upon thousands of permutations, saving countless hours in the lab making cells that just won't work. But even then, when a cell design works in simulated reality, it then has to be produced in the real world to prove its viability. The process of making a physical cell in a test environment is a time-consuming process. But it matters less if it takes days to properly coat an electrode or takes 20 tries to get the cell chemistry set up correctly, because the focus is on taking a theoretical cell chemistry from the drawing board, or rather the computer simulation, and making it a physical reality. And in the lab, the first priority is proving that the theoretical new cell actually does what it's meant to, that it can do all the things it was supposed to, and that the scientists who developed it have a pathway to replicating their successes on a larger level. Often, the initial cell design and prototyping is either supported by a university or through generous grants or investors. Turning a successful cell into a battery that can be used in a vehicle, though, is several orders of magnitude harder. And what I'm about to detail here is an extremely simplified process based on the real world. First, the cell has to be scaled, and I'm not talking about its production. When dealing with new cell designs, electrochemists tend to start with single cells, testing and refining them, before then working on larger capacity cells, and then battery modules made of multiple cells connected together. That scaling of cells and cell designs allows for real-world prototype testing, such as powering a device or a small electrical circuit under load. Every time a cell fails or performs in a new, unexpected way, more testing and examination has to be carried out. Cells are examined at the microscopic level to figure out what's going on, and that process is time-consuming and expensive. Refining a cell design can really take years. Only when multiple generations of cells have passed laboratory testing can they proceed to series production, and that usually means not only continued electrical engineering, but also involving robotics specialists, mechanical engineers, and system designers, as well as industrial partners, to ensure that a logical, well-thought-out production line is designed. That production line's job is to replicate what was done in the laboratory when the cell was constructed, but at a much larger scale. And at this stage, you can run into problems. For example, a coating process that worked well in the laboratory may simply not scale well. While it might provide even coating in the hyper-controlled environment of a small group of scientists coating single plates, at scale it might be uneven or inadequately adhered. Any number of complex problems might occur, which mean the steps of getting from a lab to a scaled production line can take a long time. Initially, a new cell design may be produced on a small-scale production line, just like Tesla did with its prototype 4680 cells that was done at its Fremont production facility before its expansion to larger-scale production elsewhere. More testing is carried out, ensuring consistency of design, consistency of performance, and most importantly, putting the resulting cells, in an electric vehicle application at least, through prototype module and pack production, validation, and testing. And of course, when dealing with prototype battery packs for EVs, that also includes a whole lot of mechanical and thermal engineering to ensure the battery pack is properly cooled and kept operating at an optimal temperature, as well as hours of programming of battery management systems to ensure packs are kept operating within the original design specifications. It also means millions of miles of simulated driving, as well as many, many more real-world test drives, where the cooling systems, battery management systems, and charging circuits are put under extreme scrutiny to ensure that the pack is performing as expected. Only when all of that has been successful can larger-scale production be attempted, and even then further testing and refinement takes place. I've already talked in a previous video about the clean room requirements for battery cell production facilities, the same kind of clean room processes that you find in a microprocessor facility. And this circular testing and quality control is essential to ensure that cells are produced that are actually good enough to be in an EV. Cells are tested automatically during their manufacturing, and then cells are even selected at random for further, manual, in-depth laboratory testing. When a cell fails, either an automatic production line test or an in-depth test, or it doesn't perform as expected, it's sent back to the laboratory for forensic analysis to figure out what went wrong. Once analysis is complete and lessons learned, the faulty cell's materials are often recycled and find their way back into the production line as fresh raw materials. You might think too that when a battery has reached this level of production and testing, that the majority of cells coming off the line are good for use in a vehicle, but that is simply not true. Every cell manufacturer, even Tesla, which has its own gigafactory specifically for producing batteries for its cars, has a pretty high number of cells that come off the line and then fail testing and have to be recycled. It's not quite as bad as my days as a professional oboist when I used to make oboe reeds. I would make 3 terrible reeds and 6 okay reeds for every 1 amazing reed that I actually used. But the amount of cells that don't ever make it to a battery pack are pretty high in every production facility that make them. The reason for this? Battery cells are designed to operate at the atomic level. And the more energy dense a cell is, the lower the tolerances between a pass and a fail become. Which brings me to the matter of why it takes so long for battery faults to be identified. Thanks to advances in computer technology and AI, designing, testing, and even producing battery cells is far easier than it once was. But most of the issues that sneak through all of that QC and make it to a physical battery pack in a car are issues that are simply not detectable through any traditional means. If a car suffers a casting failure in its suspension mount, for example, it's easy to see what's failed, and sometimes even why. Sure, engineers may break out a microscope to figure out what went wrong in the manufacturing process, to maybe see the component in superfine detail to figure out what type of break occurred and why. But if you've got a number of cars with broken suspension parts, well, it's at least a component you can see and interact with. But batteries are different. They operate on the microscopic level, and any issues with manufacturing or cell design happen on incredibly small scales. In all of this testing, engineering, and manufacturing, those responsible for the battery are working with incredibly tight tolerances. We're not talking a few millimeters, we're not even talking microns, or micrometers if you prefer. We are talking nanometer and picometer levels and smaller of measurement. We are talking using electron scanning microscopes to see things, not vernier calipers. A microscopic misalignment of a piece of production equipment that looks just fine to the naked eye may be enough to cause severe problems. It might be enough to exacerbate dendritic buildup on electrodes within the cell that are large enough to puncture through the separator material and cause internal shorts. Or it may be enough to create higher than designed internal cell resistances, heating up the cell more than expected during high charge or discharge events, prematurely aging the cell and accelerating its inevitable failure. In the case of the Chevrolet Bolt EV battery fires involving a dozen or so 2017 to 29 Bolt EVs, the fires suffered by some Hyundai Kona EVs, and many other battery fires from other automakers, both the automaker and the battery cell provider have to examine the affected battery cells with a fine-toothed comb. Or rather, an electron scanning microscope, X-ray machines, and other things to figure out what went wrong. Then they have to backtrack the cell's history, figuring out when and where it was made, and to ultimately trace things back to the point at which things went wrong. This could be a fault in the cell design, which thankfully is rare but can happen from time to time, a contaminant in the cell, as happened several years ago with a whole host of battery packs destined for Mitsubishi i-MiEV and Outlander PHEVs, a problem with raw cell materials, or as we discovered with Hyundai and LG Energy, a misalignment in one of the machines on the cell production line. Because these deficiencies can be so tiny and so hard to spot, and because when cells do fail it can lead to their near complete destruction, it takes far longer to detect and remedy a physical problem with a battery pack than it might be to detect problems with other vehicle components. In the interim, both the automaker and the cell manufacturer have to decide how to proceed with fixing and addressing the problem. It has to happen with every battery fire from every manufacturer, and to date, most automakers out there have experienced some issue or other with battery fires. Of course, the reality is that statistically, It's far less likely that a battery electric vehicle will catch fire than an internal combustion engine vehicle. And the reality is also that producing high-performance electric vehicle battery cells is a manufacturing challenge unlike anything most people will personally encounter. Things inside a battery pack are happening at an atomic level, something most humans struggle to conceptualize. And that microscopic world is completely different from the visible and easy to understand world of suck, squeeze, bang blows that drive an internal combustion engine. We've fielded some questions here at the channel about why Tesla's rollout of its new, potentially game-changing 4680 form factor batteries is taking as long as it is, given that the company first announced the cell quite some time ago. And hopefully understanding the challenges involved in scaling battery production helps make that all a bit clearer for you. The challenges of figuring out why a battery has failed, as we've seen with the LG Energy batteries in both the Kona EV and Bolt EV, only go to show why Tesla would want to make certain that everything with its new cells are as stable and as reliable as the older generations that it's been using in its vehicles for years. And while we are on the subject, let's talk for a moment about the issue affecting the Kona EV and Bolt EV. In the case of the Kona EV, Hyundai ultimately, after discovering the manufacturing misalignment that led to some cars' batteries catching fire, decided to recall all affected cars and replace their battery packs. In the case of the Bolt EV, GM thus far has tried a software fix in an attempt to identify and protect hardware before it fails. But as history shows, its initial attempts were unsuccessful. And while GM has said it will replace faulty modules and affected packs, it hasn't yet said exactly what was causing the packs to go into thermal runaway, other than to say, quote, experts from GM and LG have identified the simultaneous presence of two rare manufacturing defects in the same battery cell as the root cause of the battery fires in certain Chevrolet Bolt EVs. It also hasn't yet said how it's going to detect these faulty modules with more certainty than its previous battery pack analysis process, which, as the fires since that recall rollout have demonstrated, failed to catch all of the faulty modules. For those of us wanting to figure out what happens next to the Bolt EV battery pack, the knowledge that it often takes intense examination at a microscopic level to identify the problem is of cold comfort. Yes, as I've just spent several minutes detailing, this is complicated stuff. But it also isn't unreasonable for consumers to expect companies to have all of their ducks in a row before releasing technology to the market. And when that proves not to be true, to expect the kind of swift resolution that we've grown accustomed to in an automotive market that grew up around the far more macro-scale technology of internal combustion, as opposed to the micro-scale of a battery's innards. At the same time, as consumer demand and the demands of consumers grow explosively in the electric vehicle space, hopefully not too much of the explosions, I think we may see more issues with undertested and not entirely proven next-generation batteries finding their way into cars on the road. We can buy cars at the bleeding edge of low-cost, long-range and fast charge capabilities, or we can buy cars with older, road-proven battery technology. But I'm not sure we're going to be able to have both at once as we move forward into an electrified future. I would love to be wrong, but this is tough stuff to get right on the technology side. Getting it right on the customer care side, at least, should be better. Though that's challenging some companies that are failing too at the moment. Watch this space. And that's it for today. If you liked the video, be sure to give it a thumbs up and don't forget to subscribe to this channel and our other two channels, Transport Evolved Take 2 and Transport Evolved Shorts. We know that while a fair few of you are already subscribed, many more aren't. So go on, hit the bell and help us out. Let us know below what you thought of the video, and if you're not someone who likes the YouTube comment section, I don't, then why not continue this on our Discord server? It is free and the link is below. Thanks on behalf of the entire TE crew go out to the folks on my right for being our $15 to $49 a month Patreon supporters. Special thanks to our $50 a month patrons, that's Andrew Martin, Guido Drahoa, Brophy Wolf, Anonymous Freak, Regine Fallows, Kyle Hodgson, Gordon C, Paul Conway, Laura Sanborn, Anthony Coates, Denny Hyde, Sean Ueda and Tesla in the Gong. And our deepest gratitude to our $100 a month Patreon supporters. They are John Lyons, Marcel Ward, Reggie Watts, JP Fagerback, Will Graylian and Ian. If you would like to join the ranks of wonderful supporters, you'll find links below to Patreon, Bitcoin and Ko-fi, and of course you can also buy your very own TE swag at our Redbubble store. Thanks for joining me, and as always, keep evolving!